Okay, we're going to be covering solids and modern materials, and this will be the first 3 sections of Chapter 12 in Brown LMA. Alright, so the first thing we're going to do is talk about classifications of solids, and we have several different kinds. Remember, solids, all the solid particles have to be close together. While they have some energy, they don't slip or slide past each other. They're just held pretty much in a static position. So we have metallic solids, and these metal atoms are held together by a sea of electrons. Okay, so they're actually shared valence electrons, but all of them for each atom will always be neutral. And examples of our metallic solids, of course, would be copper, iron, tin, gold. Ionic solids we've talked about and worked with in the past. And those are held together by ionic bonds. So those are charge attractions between cations and anions. When we talk about covalent network solids, so you have a bunch of covalent bonds between the atoms that are holding them together. So diamond, graphite, those are all covalent network solids. Now, how is that different than molecular solids? Within the molecule, those have covalent bonds. So the atoms in a molecule, like in water, the hydrogen to oxygen is held by a covalent bond. But to hold the molecules together, they are held together in a solid as in ice by intermolecular forces. So we're talking about the London dispersion forces, the dipole-dipole, the hydrogen bonding. And because those are so small compared to some of the others, that's why when we look at molecular solids on a whole, they tend to have much lower melting points. So if you look at the melting point of an ionic solid versus a molecular solid, so ice versus sodium chloride's melting point is going to be way up in the thousands of degrees Celsius. Now, other types of solids that we'll only mention here, but we won't go into too much detail at all after this, for this semester, are like polymers, and they're made of repeating units, and each of those units, a repeating group of atoms, is called a monomer. And plastics like high density polyethylene, the HDPE that's got a recycling code of 2, those are polymers. Biopolymers like the proteins and the DNA that's in your body, those are all polymers as well. Nanomaterials, when we talk about the fullerenes or the nanotubes, those are more of the man-made materials. But we can also have like nanoparticles of gold, clay. Those are also nanomaterials. And if you look, the crystals themselves are small. They're like 1 to 100 nanometers in size. So when we talk about solids, not only do we classify the types of solids now, we also have to look at their structure, and we have what we call amorphous solids and crystalline solids. So amorphous solids don't really have a repeating geometric shape. Okay, obsidian, of which I give you an example here, which is glass. Glass is an amorphous solid. Okay, rubber, your hair. Okay, those are solids, but they don't have a repeating geometric form. Crystalline solids have a repeating 3-dimensional geometric pattern, and sodium chloride, diamond, table sugar. In fact, this is actually brown table sugar. So you can see that there's some impurities in there that make it look brown. But you can see it has a geometric pattern to it that you can actually see. So a lot of the crystalline solids, when they have the geometric pattern, they will have flat faces on their crystals when we look at them. Okay, I mean, in fact, if you go back to diamond, when we find diamond, it looks a lot like this, and it's only when we cut and polish them that they have that brilliance that you see in jewelry. And one of the things about diamond being as hard as it is, though, we have to be careful in investigating the planes, because we can cut it, and if we cut it in the wrong plane, we can shatter a very beautiful rough diamond. So understanding how to look for those 3-dimensional geometric patterns is really important. Okay, so how do we describe a solid? Okay, and how do we describe its geometric patterns? So what we do is we use this system with unit cells and crystal lattices. Okay, and I I show you a crystal lattice in 3 dimensions, which is what we would use. Okay, I show you the unit cell in 3 dimensions. But just be aware, nature, while we have a reference system so we can talk to each other about it, nature doesn't require that everything has to be 90 degrees. But we're going to focus on that. And if you like this topic, then I would pursue it in terms of studying up on X-ray crystallography, because that's where we use this all the time. Okay? So here's your crystal lattice, and all we're doing is trying to set up our coordinate system in which that we can describe our structure. And in our coordinate system, the smallest repeating unit is called a unit cell. And how do we describe that? We describe it by the length along the x-axis, the length along the y, the length across the z-axis, and if you look at the angles between B and C, is alpha, beta, and gamma. So with those 6 different variables, we can describe any unit cell and crystal lattice. Okay, so I'm going to give you some examples of the 2-dimensional lattices. They're called Bravais lattices, and also the 3-dimensional, just so you get a feeling for it. What we're used to in graphing is just having a coordinate system where A is equal to B. And all my angles are 90 degrees. So this is like your typical graph paper when you make a graph. Okay? Now, but we're not restricted to just doing our lattice points this way. What happens if this unit is not the same as that one? Then it's rectangular primitive. Okay? What happens if my angle, look at this distance is equal to that distance, but my angle is not 90 degrees. So now is 120 degrees. And we call that hexagonal. But our unit, our repeating unit, the smallest repeating unit, has 4 signs to it. This is less than 90 degrees, and A is not equal to B. So these two look like your rhombohedrons, right? We have what we also call body-centered, or this is rectangular-centered, and that's if we bypass one of the lattice points, it's a rectangle, and we have this point right in the center. But if you look at it, this is really at the 4 points. So rectangular-centered is like taking these 2 combinations, okay? So we can do rectangular primitive, we can do rectangular centered. All right, so when we look at the 3D lattices, we have cubic. These are all cubes, all right? And we can put, remember how we did, let me just go back really quick, how we skipped and had a point right in the center? We can do the same thing with 3-dimensional lattices. If you alternate and just like miss one row, you can have one of your lattice points right in the center. So this is body-centered cubic, because we're making a cube. This one's cubed as well, but it's very dense, and we're missing not just a single line, but a whole plane that has 4 units in there. So you can see 1, 2, 3, 4, 5, 6. So on each face of this cell, I have a dot. This is called face-centered cubic, because you have a dot on each face. So you can have different unit cells, okay? And then you can also have those dots that are on the side, only face-centered, body-centered. But we're really going to spend most of our time, actually, the rest of our time, focusing only on cubic. Okay? So let's go through an example. So here, we're going to do a 2-dimensional example. Here is my crystal lattice. You can see all my points, the lattice points, and this is my unit cell. It's described by this length, and the angle gamma. Okay? And what happens is when you have your structure, what we're going to do is that when we do crystallography to get the structure, you're going to get a motif. And a motif is an arrangement of atoms in the cell. And when you line up what we call tessellate, and I'll explain when we do that, your unit cells, okay, you're not required to have a single molecule in here. What you're required to do is to have a motif, an arrangement of your atoms so that when you line them up, it repeats so that you actually can build in your whole molecule and your whole structure. Okay, so we put in a motif in this. That's my motif in my unit cell. Now you can see, just like we were saying, you don't have to have the whole molecule. It has to be in there somehow related so you can tessellate them, connect them. But look at this guy doesn't have his hooves. He doesn't have one of his legs. Okay. Oh, but there's a leg. But where's the rest of the Pegasus? Right? What's this brown stuff? So we're looking at just repeating patterns. Okay. So kind of just take a step back and say, okay, I know it's not a molecule right now. I just need to see, is there a pattern in here? Okay, so then you put your pattern, your motif, in this crystal lattice. So when we do our crystal structure, okay, we come up with our motif, and we come up with our crystal lattice, and we try to match the two. So that once we start repeating it, you can start seeing, okay, now I was like, oh, now I'm beginning to see the whole pattern here. Okay, I'm beginning to see at least the cream-colored horse. My bays aren't quite there yet, or actually these are chestnuts. So my chestnuts actually were not quite whole yet. I've got to complete the whole thing. Now when you line them up, this is called tessellation. And there are certain things that you have to know about your geometric structures. We'll just talk about 2D for now. When you look at anything that's four-sided, like a square or a rectangle, okay, with a repeating pattern, they can tessellate pretty easily. And you see there's no gaps in between as I fill it up. If you look at hexagons, so if you look at a bee's hive, and you look at all the hexagons in there, okay, that they store the honey, that they store all the baby, the larvae, and stuff like that, those tessellate really well. 5 pentagons, so 5-sided shapes don't tessellate. Okay, it looks like it on a soccer ball. You'll see it's got pentagons everywhere, but if you look at the top of your soccer ball and the bottom, they would be hexagons because you'll be forming gaps. Okay, so just be aware, whatever type of unit cell you make, it has to be able to tessellate, to be able to repeat without having any gaps. When we're done and we put in all our unit cells, you can see how we're trying to repeat the same thing. This is missing a leg, but in the other cell, at the very top, is his leg. He's missing his hindquarters, but it's right here across multiple cells. Okay, so when we put all of our unit cells together in our crystal lattice and line them up, now you can start seeing our whole structure. Okay, and if I remove my crystal lattice away, it's just like, here's my solid molecule. This is what it looks like. And you would see all your Pegasus here, your brown ones, the chestnut ones there. Okay, and that's how we get crystal structures. So that's why it's really important. So you should know your basic cubic unit cell, the primitive cubic, the body-centered cubic, and the face-centered cubic. So this is what, when I said we'll be focusing on it. This is your primitive. And this basically, if you do a space filling, you can see how at the corners, I only have 1/8 of an atom. Doesn't mean that you can actually cut an atom. This is what my structure looks like. But when we line up our cells together, you will build your whole atoms at the end. But right here, you're going to be repeating it across. So that's a way of just developing our coordinate system. This here, I have a body-centered cubic cell, and here I have a face-centered cubic cell. And this is what it looks like when you start putting your lattices, building your lattice. Okay, so that's how it packs. All right, there are several different ways to pack, and you can read about that, but the most important part is just knowing how it stacks up. And so that's how we actually get a true crystal structure. Now, if you notice on my primitive cell, cubic cell, okay, it's 1/8 of an atom. So one cell, if I have 8 corners, basically one cell has 1 atom. Okay, and we're going to be starting to focus on our metallic solids. if you look at the body-centered cubic, it has 8 corners, so 1 atom and 1 in the center, so 2 atoms per cell. And the face-centered, I'm going to have 4 atoms per cell. A little more dense. So primitive cubic is the least dense. If I have a unit cell that has 4 atoms, it's pretty dense. It's got a lot of atom in there. Okay? So basically, now that we've talked about how it looks like for our metals, okay, so what's nice is our metals. If we look at some of our other compounds, like the metallic solids or ionic solids, it doesn't mean that every single atom has to be on the corner. But our metal solids, which we started working on, okay, when we started focusing on the cubic unit cell, okay, it turns out that for metals, our atoms fall at these points. Now, if you want to know the primitive for metals, the primitive isn't that common. Polonium is probably a good example for the primitive. For the body-centered, you would be looking at something like copper or sodium. Okay, and we were talking about how dense this was. Then you're going to see like lead. You're going to see silver. You're going to see gold. So you would see that more commonly in those. Okay. Now the last part that I want to get to will be alloys. Okay, so alloys, remember, they're basically mixtures, all right? And it's so you know it's going to be variable composition between different types of alloys, and it's for these 2 types that we're going to talk about, and then the next slide I'll show you ones that aren't homogeneous. It's going to be basically uniform in terms of the dispersal. It's not like a structure, like a compound structure, but uniform in the sense that if I took a small aliquot of my alloy, it would have the same percentage, okay, of components. All right, so what is an example of a substitutional alloy? 14 karat gold, bronze. And what's an example of interstitial alloys? It's steel or stainless steel. What is the difference between the two? For substitutional alloys, I substitute one of my solvent atoms in the crystal structure with a solute atom. In an interstitial alloy, let me go back and show you see how there's gaps here, 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 there's spaces here. Okay, so in interstitial alloys, the solute atoms have to be fairly small that they can fit in the spaces. Okay, so as you can see, this is my gold, or brass has tin and copper. Okay, or zinc, bronze is tin and copper, brass is zinc and copper, and they're about the same size. So instead of just having everything as a copper atoms, all my copper atoms here, the zinc fits in the same space where copper is. Okay, so anytime I have a copper, I'll have a bunch of coppers, but then every once in a while, a zinc replaces it. Okay, interstitial, because of all the spaces in between here, for the interstitial, you're going to see little itty bitty spaces are filled with the carbon. So when you look at your alloys, one of the key parts is this. Look at what your solutes are versus solvent. So for like 14 karat gold, silver and gold are approximately the same size. So the silver can't fit in the spaces. Silver will end up substituting for the gold atoms. And so that is a substitutional alloy. If I had something like, let's say palladium and boron, okay? Boron is a small atom. So when you look at something like palladium and boron, then what would happen is the boron, being small, could fit in the spaces. And that's why actually steel is interstitial and not a substitutional alloy. Because here, carbon is so much smaller than iron, it can fit in the spaces. Okay. Now, is there a small distortion when that happens? Yes. Yes, of course. It's kind of like if you have sheets of paper, or and then you have like a couple paper clips slipped in between. It can fit, but you'll see a small distortion. In my opinion, best thing is if you've ever seen The Princess and the Pea. It's like this is her mattress, and these are the peas that can fit right in between the 100 mattresses, right? And there's a small distortion. Okay, so those are interstitial alloys. Is basically steel, and then substitutional, like I say, brass, bronze, even pewter, 14 karat gold, 10 karat gold. Okay, two other types of alloys that or metals that I want to talk about are heterogeneous alloys. And what happens is we have two different types of structures with this. So you're going to have chunks of just pure iron, and then interspersion there in a non-uniform matter, chunks of a compound called cementite, which is iron, 3 iron, and a carbon. So you can actually, if you take small slices and look under a microscope, specifically to look at structures, you can actually see the different types of structure, okay, throughout this heterogeneous alloy. So perlite is an example. It's not the only one, but it is a good example of a heterogeneous alloy. Okay. And the last set of things I want to talk about are the intermetallic compounds. And it's like your nickel aluminum, okay, your niobium tin. And what happens there is that they're actually compounds. They have a definite composition. 3 nickels for every aluminum, okay? It does give you much better structural stability because it's like a crystal structure, that you don't have any type of oh my goodness, distortions or anything like that. If you see interstitial or substitutional alloys, it has a much higher melting point. So you can use these types of intermetallic compounds for much higher temperature applications. But the one thing is they are more brittle, okay, than substitutional alloys. So they'll break more easily once you get to that strain, to the point where they get strained. That's going to be the end of what you need to know for Chapter 12. And we will move on to equilibrium.